I will be giving an overview of the Aquatic Habitat Assessment plugin tool, which Marisa and I have been using in our Santa Clara project in California. And in this presentation, I'll be giving some background info for things that you need to understand Aquatic Habitat Assessment, or AHA. The input data you need to enter into WEAP in order to use AHA. And then if you run it, I'll be talking about the results that you get from it. And what I hope that you all will get out of this presentation is mainly the basic concepts of AHA. It's a fairly complicated tool, and I've done my best to break it down, but to some extent, I hope that this recording and this slideshow can kind of be used as a future reference as well. But for now, I just hope you all can sort of understand the basic concepts of it, and especially for Uttam and Tanya, just kind of thinking, is it the right tool for you? You know, is this based on the needs of your project? Is this the appropriate tool? And if it is, I hope that you'll be able to start using AHA and WEAP. And like I said, it's fairly complex. So, of course, I expect that you'll have questions about how to use it. It's not easy. It's definitely a challenge. But after this presentation, I hope that you know enough to know how to ask the questions. And like I said, you can use kind of the more advanced details in this as a reference. Some things might make more sense as you're trying to use the tool and getting into it. There's a README when you try to download the plugin in WEAP, which I'll show you. And of course, you can always ask myself or Marisa directly if you have questions about using it. And since it seems like a lot of people will be using the recording, and just to kind of keep the flow, I expect that you all have questions, but please save them for the end, and then we can go into a question and answer session, and I might even be able to give a live demo of the tool. So with that in mind, let's look at the background info that you need to understand the tool. So accessing AHA. It's a WEAP plugin, and you can go to the plugin download menu in WEAP. And at this location, you can find a README, which has a lot of information in these summary variable notes tabs. And if you download the plugin in your WEAP model, you'll have many new variables. It says 64. So that's sort of tying back to where I said the tool is fairly complex. And then what is the purpose of AHA? AHA quantifies the biological suitability of stream habitat for aquatic species in WEAP. You know, when we run WEAP, we're often looking at different water management scenarios. And AHA basically is the biological connection. It then asks the question, given these water management scenarios where we have different flows at different times, is the habitat better or worse in certain scenarios? And you can run it on a daily or monthly time step. The daily is definitely recommended if you can do it, because a lot of the fish conditions can vary daily, and that really does affect the biological health. And the results are broken out according to a few different parameters. The plugin looks, and the examples I'm showing will be those that we have from Santa Clara, which is near San Jose, California. And they're customizable. So the examples I'm showing will be what we designed it for, but you can definitely customize any aspects of these that you need. It looks at different aquatic species, so you can look at multiple species. We looked at salmon and trout. Biological life stages, which I'll be describing these in greater detail in the next slide. It looks at the suitability of the different conditions. Is the depth, velocity, or temperature good for the fish? And then it looks at different habitat types, different sections of the river. You can have riffles or runs or pools. And the suitability may be different in each of these habitat types. So again, AHA is kind of the biological connection to quantify how good is the fish habitat. And it will look at the different species, life stages, conditions in the stream, as well as the sections of the river. And then going into greater detail, the biological life stages, I'll be describing at least how the life stages work for the California salmon and trout. And it's important to understand these life stages to really understand the purpose of the tool. So these fish live most of their lives in the ocean, and they travel up these cold coastal streams to reproduce. So the first life stage is adult immigration, where the fish travel upstream. And then once they're in these cold headwater areas, then they spawn and lay eggs. The eggs grow in the stage that we call embryo incubation. And then the eggs grow into small fish called fries, which feed in the headwater areas. The fries keep growing until juveniles. And then eventually the juveniles, when they're large enough, emigrate out of the stream and return to the ocean, where they live. They grow and they feed in the ocean. They live most of their lives there until eventually they return to the same stream system to reproduce. So a beautiful circle of life. So with that in mind, what does AHA actually calculate? I'll be giving kind of an overview of the results. And again, this will be the part where there starts to be a lot of details to take in at once. So I asked just try to grasp the basic concepts and know that we'll be talking about these things later on in the results section as well. So AHA calculates indices for basically two types of results. We have habitat availability and passage. So habitat availability results, it quantifies the surface area of biologically suitable habitat. So how much good habitat is there for the fish species? And then passage looks at, can the species travel up and down the river? And these result types are different, applicable for different life stages. Habitat availability looks at, is the habitat suitable during the life stages of laying the eggs and then the fish growing, all in those headwater areas. Whereas passage looks at immigration and emigration, and can they travel up and down the river back to the ocean. And they also look at different places in the river schematic in WEAP, which when using this tool, we have entered in different POIs or point of interest along the river. So certain important points, whether for habitat or passage, are entered here. And the passage is determined at each of these POIs. So can you travel up to POI 1? Can you travel to 2 and then 3? In between these POIs are river reaches. And within each of these reaches is where the habitat area is calculated. So how much suitable habitat is in reach 2 and how much suitable habitat is in reach 3. And lastly, these two types use different habitat parameters. So habitat availability takes the average depth and velocity of the stream, whereas passage takes what's called the fallweg depth and velocity, which is at the deepest part of the channel, because the assumption is that the fish, as long as the deepest part of the channel is deep and moving, that the fish can pass through there. So this is kind of a brief background of some of the concepts used in the plugin, as well as the result types. And we'll get into a little bit more detail in these results later on. So now we've talked a little bit about the background info for the tool. So hopefully you all have a kind of a basic grasp of the types of concepts the tool deals with. And now we'll talk about, if you want to use this tool and run it in WEAP, what input data do you need to put in? And I will say, it's a lot. It's a lot of data. It's not necessarily easy. And I won't say that it's unique to this tool either. When you run these biological models, you're very concerned with both the biology and the stream morphology. And that's fairly data intensive. And that's true for any type of biological model like this. So with that in mind, the first input you'll need is what's called life stage timing. And you need to input this into WEAP, which defines when is each life stage active. And in Santa Clara, we used a representation that looks like this, where in WEAP, we set it active each life stage for certain months. And what this does is the results in WEAP are only calculated for the life stage when it's active. And as you see below, it varies by species. Often in the US, we have what's called fall run salmon or winter run salmon. So these parameters allow you to kind of customize the months and the times when each life stage is active. And then you'll also need to input data related to the physical habitat. So this is data related to the river reaches. And what you'll need to do is populate the flow depth velocity relationships. And these look something like this, where for any given stream flow, you have a corresponding depth in the channel. And WEAP uses these relationships to calculate the hydraulics. WEAP will model the stream flow, and then it applies the relationship to estimate the depth and velocity. And what we did in Santa Clara was we used a cross-section hydraulic model called HECRAS to help with this process. We actually modeled the stream channels in HECRAS to find these relationships, which we then entered into WEAP. So again, this is, admittedly a fairly lengthy process, but this is true of any cross-section model like this. The next thing to do is to calibrate the temperature, which populates the temperature parameter in WEAP. And WEAP does have an internal temperature calculation routine, which you can use that, but you'll need to calibrate a few of your parameters first. What we've also done in Santa Clara, we've used both of these. You can run an external temperature model or form an empirical regression as well and import that into WEAP. So there's multiple methods to get the temperature. It is optional, I suppose I could say. It's not every model has any data related to temperature, which can make it hard, I understand. But it really does, depending on your fish species, it does reduce the analysis that you can do. You could choose to run it with all flow. So temperature is optional, but it's definitely recommended. And then finally, you can enter river habitat data, which generally comes from stream surveys. And this will let you populate things like the substrate in the stream, the cover, and the surface area of the different habitat types. So again, these are all of the inputs you need for the physical habitat related to the river reaches. And next is the inputs you need for what's called the habitat suitability indices, which this is basically the biological data that you need. And it looks something like this. We call them here habitat suitability indices, or HSIs. I think I've heard the term biological suitability curves as well. And what it is it asks, are the habitat conditions biologically suitable for a given species? So for a range of velocities, we have a range of suitabilities from 0, completely uninhabitable, to 1. So this is basically saying, what are the tolerable velocities for the fish species, and which velocities are actually ideal. And you need a lot of these relationships, the different parameters compared against the suitability. And you need them for each species as well as each habitat type. So that's riffle, run, and pool. And they apply each for one life stage. So you might have a different suitability for spawning as opposed to rearing. Maybe the fish that are already born can survive, but the fish aren't able to lay eggs in those conditions. And again, you need these for each of these stream conditions. So looking at depth, velocity, temperature, cover in the stream, and substrate. And you'll see that not every condition applies to every life stage. So this also tells you how these life stage results are calculated as well. They look at the suitability of each of these check marks. And in addition, there are also biological inputs you need for the passage life stages as well. But these are a little more simple. These are only a threshold, where it's just a minimum depth that you need, or a maximum tolerable temperature. So it's a little more simple than these HSI curves. And this again is the biological input data that you'll need to run AHA. So this is the last section. And what we've talked about until now is the inputs that you need to get the tool to run. So now that we've entered our inputs into our WEAP model and we've run it, what do the outputs look like? What are your results and what can you do with them? And I'll tie back to this slide that we looked at previously, where I want you all to remember that we have two types of results. We look at the habitat availability, which is how much good habitat do we have in each of the river reaches. And then we have passage, which asks, can you migrate up and down the stream back to the ocean? And these are the types of results that we'll be diving into. We'll be looking a little bit more at habitat availability and then a little bit more at passage. So first, we'll talk about the habitat availability indices, which is in the results, it's HAI. And again, this quantifies the surface area of the habitat in each river reach. And within each river reach, during our inputs, we entered the amount of surface area for riffles, runs, and pools, which are the different types of river reaches and different types of habitat. And these allow us to calculate the HAI, which is an aggregate value of the HSI and CHSI. So there's a couple of intermediate results, and depending on what you're interested in, you can choose to just use the aggregated results or the intermediates. And this is another slide where there's a lot of details, so try to just grasp the main concepts. And by the time that I finish the slide, I think the details come a little bit more clear. And also, we're getting close to the end, so you'll be able to ask the questions soon. So the first result is the Habitat Suitability Index, the HSI. This is what we discussed in the previous slide. It's the initial result, and it just comes from these biological curves where we have the parameter that is modeled in WEAP, this example, velocity. And using this curve, we get a value from 0 to 1. And again, it uses all of those HSI curves, the biological suitability curves. And an example of this is you have on a given day, January 7th, on a given reach, reach 2, for a given species, Chinook, a given life stage, rearing, and then a given habitat type, riffle, you have an HSI. So there are many, many of these results that are generated. And in this example, it's 0.7. So it's close to ideal. And the next step in the results is that these HSIs are aggregated into composite HSI, where the results are aggregated across all the stream conditions. So that's things like velocity, depth, and temperature. And this will give us, instead of a riffle velocity HSI, now we just have a riffle CHSI. And again, it ranges from 0 to 1. In this case, just an example, it's 0.43. And it's calculated by essentially multiplying the HSIs for each condition, so velocity, temperature, depth, and cover. And the way to think about that is the fish needs tolerable conditions for each of these to survive. You know, if you have a very suitable velocity and a suitable depth, but your temperature is completely uninhabitable and it's 0, then it won't matter. The composite HSI will be 0. Whereas if you have good conditions for all of these, then you'll have a good CHSI. And then the last step is to aggregate it a step further to get the habitat availability index, or HAI. And this is the most aggregated value, and it aggregates the CHSIs across all habitat types. So that's riffle, run, pool. And it also changes it so that now it's in units of area. So our example here is that now, instead of having our rearing riffle CHSI, now we just have a rearing HAI. So that's one value for each life stage for the entire reach. And we'll also see that instead of the value from 0 to 1, now we have value in terms of the area, which that is basically the value of 0 to 1. So it's each of the CHSIs, which range from 0 to 1, multiplied by the area of each of the habitat types. And I know that there's a lot of information on this slide, and believe me, if it didn't take a lot of research for me just to finally understand really what was these 3 different result variables. So just know that this can also really just be used as a reference, as I keep stressing. You don't have to understand all of this now, but I hope that this slide at least gives you the basic details of how the results are calculated. And again, we have 2 types of results. So this looked at the habitat availability indices, and the final slide looks at the results for the passage indices, which again, the passage indicates, can the species effectively migrate up and down through the POIs during the immigration and emigration? Which we have our POIs throughout the river, and they're each associated with river miles of how far you are from the ocean. And in adult immigration, we have a result variable called adult immigration, and it asks, can the adults immigrate from the ocean to the given POI? And the value is either 0, meaning no passage, or 1 passage. So it's yes, no, or binary. And so basically it looks at, can you travel from the ocean to the first POI? Yes. If yes, then can you travel to the second POI? And if yes, can you travel to the third? And to calculate, it looks at, is the thalweg depth deep enough according to that threshold we saw? And is the temperature sufficiently low? So it looks at those thresholds that we talked about before that we input. A very related variable is called adult passage extent. And this is sort of an aggregation of the adult immigration, where it asks, what's the furthest upstream that they can immigrate to for the entire stream? So we have 1 value for the whole stream instead of the POI. And now our value is expressed in terms of river miles. So can we get 10 miles or 25 or 32? And then the answer is our value. And the calculation is the same, looking at the depth and the temperature. So now for the life stage of emigration, when we're traveling out of the stream, the variables are very similar. The one called juvenile emigration asks, can juveniles emigrate from a POI to the ocean? And the values again is either 0 or 1. And it will look at, is it deep enough and is the temperature low enough given the thresholds? And the thresholds can also be different. These for immigration can be different for emigration. So juvenile immigration will ask, can POI 3 travel to the ocean? Can POI 2 and can POI 1 travel to the ocean? Giving yes, no for each of them. And then finally, there's what's called juvenile emigration frequency, which similarly kind of aggregates the results for the whole stream. And it asks, can juveniles emigrate from the headwaters to the ocean? So is there complete emigration across the whole stream? Yes or no? And the calculations are the same. So these are the results for the passage indices. And I hope that this slide can be a reference as you go on to use the tool. Thank you all for listening.